So, welcome to this lecture 9, which is based on work and energy concept inside the thermodynamics. So, let us start this lecture. Wait, I'm trying to show you PPT. Yes. So, this is the topic, work and heat transfer. And so in thermodynamics, we talk about two types of energy interaction. The first one is by work transfer, and the second one, that is by heat transfer. And in starting lecture, that is based on introduction of basic concept of thermodynamics, we have already discussed that thermodynamics is the study of work transfer and energy transfer from system to surrounding or surrounding to system. So this is the explanation of that definition, that in a closed system and its surrounding can interact in two ways. That is the first one, it is by work transfer and by heat transfer. We also know that system and surrounding can disintegrate by its boundary. So these two, work and heat, both are boundary phenomena, because this work and this heat both can transfer from system to surrounding and surrounding to system through boundary. Okay, so let us start from work transfer. As all of we know that in mechanics, we know that work is defined as the action of force on a moving body is identified as work, or we can say that the work is done by a force as it acts upon a body moving in the direction of force. So this is the definition of mechanics. This is the definition of force inside the mechanics. Okay. So in other words, we can say that work is one of the basic modes of energy transfer. In several times, we express work like work is another form of energy. We can convert kinetic energy or potential energy into work, or work into energy. Okay, and this concept is known as, inside the mechanics, that is work energy theorem. Okay, so like that, if we talk about work transfer inside the thermodynamics, we can say in thermodynamics, work transfer is considered as occurring between the system and the surrounding. Okay, so now I am explaining this concept in detail. Okay, see that in mechanics, if we want to define work, then we know, suppose this is a system, this is any system. Okay, and if we apply force in forward direction, this is a pulling force. Okay, this is the pulling force. So if we apply this pulling force on this body, that is something body A, then this body will try to move in a forward direction. And if this body move from this state to this state, and this displacement is something delta S, then we define work that is equal to F dot delta S. Okay, work is a scalar quantity. So if we define this dot product between two vectors, force and displacement, that is equal to work. As we know that dot product is defined as F as cos theta, where theta is the angle between force and displacement. So if we talk about this linear displacement, and this linear displacement is a lie in the direction of pulling force. So in particular this case, theta is equal to 0. So cos theta, cos 0 is equal to 1, and that's why we can define work is defined as simply product of force and displacement. Okay, so that's all about mechanics work. But if we want to define thermodynamics work, okay, so this is a system. Okay, this is any system, thermodynamic system. And if we talk about contents of this system, in this system, this is a battery. Okay, this is a battery, and one motor is placed inside the system. Suppose this is a positive terminal and this is a negative terminal, and there is a one motor which is driven by this battery. Okay, and through this motor shaft we engage a fan. Okay, so this is a system, this is a system, and this is a surrounding, and this is boundary. Okay, so we clearly see that this boundary disintegrate between system and surrounding. So inside the system there are two contents. That first one, that is battery, which produce power, and that is motor, which trying to rotate this fan which is lie outside the system. Okay, so we can understand this concept that here motor trying to rotate this fan. That means this work, this is a work which is consuming to rotate this fan. Okay, this is an example of work transfer. We produce power to this battery, and this battery power go inside the motor, and this motor convert this power into mechanical energy, and this mechanical energy is try to rotate this fan which is placed outside the system. So we can clearly see that this mechanical work is consuming to rotate this fan which is outside the system. So in simple words we can say there is a work transfer from system to surrounding. There is a work transfer from system to surrounding. Okay, if we remove this fan, okay, if we remove this fan and we placed a weight and pulley, a weight and pulley, okay, this is a weight and pulley, and trying to lift this weight to this motor work, then this is the original example of work transfer in which whole soul effect will consume to lift the weight through this pulley which is placed outside the this system. Okay, so in a simple words we can say work is producing inside the system, but this work transfer from system to surrounding is consumed to lift this weight through pulley. Okay. So by this example, we can say this is an example of work transfer from system to surrounding. Okay. This is an example of work transfer from system to surrounding. So we can say very important thing is that work is said to be done by a system if the sole effect on things external to the system external to the system can be reduced to rising of a weight. Okay, this line is very important, that work is said to be done by a system if the sole effect on things external to the system can be reduced to raising of a weight. In a previous example, we already discussed that work is consuming to lift this weight which is placed outside the system. Okay, so this is the example of work transfer from system to surrounding. Again, we move towards our slide. Wait. Yes. So in this expression, we define in thermodynamics, work transfer is considered as occurring between the system and surrounding. When work is done by a system, it attributably taken to be a positive, and when work is done on a system, then it is taken to be negative. That means if work is done by system, this is the in a last example we already see that work is producing inside the system and that is consuming to lift the weight which is placed outside the system. So this is the example in which work is done by system. That is the example in which work is done by system because the weight which is placed outside the system. Okay, and we are trying to lift this weight. So this is the pure example in which work is done by system and we take it as a positive. And if in a reverse manner, if we define work, when work is done on the system, suppose something external force we apply on a piston cylinder assembly, and this external force try to compress the piston, an external force which is trying to compress the system. That is the example of negative work in which work is done on a system. So these two examples which define work transfer as well as its direction, and whatever we If work is done by the system, then we treat it like a positive work. And if work done is lie onside the system, so we can say that work is negative. Okay, so that's about work. Now we move towards displacement work. What is displacement work? Okay, so again, we have to consider piston cylinder assembly. Okay, so what is displacement work? One form of mechanical work frequently encountered in a practice is associated with the expansion or compression of a gas in a piston cylinder assembly. During this process, part of the body, the inner face of the piston, moves back and forth. Therefore, the expansion and compression work is often called moving body work or simple body work. Okay, I am trying to explain this. See. Suppose we consider a piston cylinder assembly. Okay, this is a cylinder and this is a piston. So this is a piston and one gas is filled inside the piston cylinder assembly. Okay, so what happens if we transfer heat from external heat source to this system? Then this gas tries to expand inside the cylinder. So this is the state 1. Okay, and, sorry. So initial state, that is 1. Now when this gas is expand from this state to this state, that means second state. Okay, this is the second state. Okay, so when this gas is expand from state 1 to state 2, we consider the difference between these two states, that is something delta S. Okay, so between two state distances, that is delta S. Here the cross section area of piston, cross section area of piston is A. Okay, and if this gas is applied P pressure force during expansion process, pressure, sorry, this is a pure pressure, not pressure force, pressure P of gas. Okay, this is a during expansion process pressure. So if we want to explain work which is done by this gas against the atmosphere, because atmosphere pressure is trying to prevent this expansion process. Okay, atmosphere pressure is trying to prevent this expansion process. So in this example, if we want to define work, so as we know, work is defined as force multiplied by displacement. Okay, work is simply defined as force multiplied by displacement. And if we want to define this term, force, So force is defined as P multiplied by A. That means pressure and area. All of you know that. Okay. So if we put this value in this expansion, so PA, this is a force multiplied by S. Okay. This is defined as W. Okay. If we define this term, A multiplied delta S, this is the area multiplied by change in length. Okay. That means during expansion process, what is the displacement? This is the displacement. This is the displacement. Okay. So if we define this product, so simply we can write, W equals to P multiplied by delta V. Okay. That means work is defined as product of pressure and change in volume. So because this change in volume is associated with this displacement, that's why this work is known as displacement work. Okay. So displacement work is always assigned with closed system in which boundary is moving. Okay. So in this example, we clearly see that these cylinder walls are fixed. Only one side wall, that is this piston, is moving. So this is the example of moving boundary. Okay. So in only moving boundary cases, we see this displacement. So in such type of cases, we define displacement work, that is the product of pressure and change in volume. Okay. So if we draw pressure volume curve like that, this is the pressure axis and this is the volume axis. Okay. And suppose in the first state volume is less in compared to second state, so we define this expansion like that. This is the expansion process. In initial condition, this is volume V1 and this is volume V2. This is state first and this is state second. So clearly you can see that in state 1 volume is less in compared to state 2. So if we draw this process in PV diagram, we clearly see this is the example of expansion process in which volume is expanding. Okay. So in this case, we define this process like that, V1 and V2. If in a whole process, volume pressure force is a constant, so in that case, we define this expansion process like that. This is V1 and this is V2. Okay. This is the constant pressure process. Okay. So these are the examples in which piston is moving. Okay. So if we consider one small split, this is the small split, something, suppose you assume dV. Okay. So if we define this expansion with respect to this strip, what is a work? We define, that is defined as dW equals to PdV. Okay. And if we want to calculate whole work which is consuming during this expansion process 1 to 2, So we have to integrate this expansion. Okay, we integrate this expansion from V1 to V2. Okay, this is the expansion, very important expansion. This is valid for closed system. This is valid for closed system. And again, important term, it is valid for quasi static process. Okay, this expression is defined for closed system, and this expression is valid for quasi static process. What is quasi static process? We already described this term in previous lectures. Quasi static process is a process in which state 1 to state 2 transformation is live in a very slow manner, because we want to define maximum equilibrium, intermediate equilibrium stages between first and second points. So for getting maximum equilibrium stages, we have to transform this state 1 to state 2 process in a very slow manner. Okay, in a very slow manner. And if we performing this transformation in very slow manner, we get lots of equilibrium stages. Okay, that is 1, that is 2, that is 3, that is 4, up to n. Okay, so for such type of process, we define clearly process path which connect state 1 to state 2, because this expression is totally depends upon which type of process path will followed by the system for state transformation 1 to 2. Okay, in other words, you can say that this indication suggests that if you calculate area under this curve, okay, if you calculate area under this curve, area under this process path, this is known as this value dw. Okay, if you want to this integration means that is the summation, and summation means if we expand this straight, okay, so area under this process path on volume axis suggests to you what is the work done in this process. Okay, so, because this work is totally depends upon the process path, so that's why if path is changing from state 1 to state 2, work is also changing. So again we move towards our slide. Yes, so in this expansion we already see that this W is defined as F dot ds, or simply we can say F is the product of pressure and area multiplied by ds. And if we define this term A multiplied ds, that is equal to change in volume. Okay, so and P, this P is known as absolute pressure. We already discussed this term. What is absolute pressure? Absolute pressure, that is the summation of pressure, atmospheric and gauge pressure of the system. Okay, so as an expansion for boundary work output WB out, a negative result indicates boundary work input compression. That means if this process is in expansion process, okay, if this piston is trying to expand, that means work is done by the system and against the atmospheric pressure. So this is the case of positive work. And if we talk about reverse process, in which this piston is tries to compress, okay, against the gas pressure. If this piston is trying to compress against the gas pressure, this is the example of negative work, because in which work is done on the system. Okay. Now we move in next slide. This is the boundary work. So in this figure, we connect PV diagram with displacement of piston cylinder assembly. So this is the first state and this is the second state. We consider a small spirit between these two stages. This small spirit is defined as a dV. So if we connect with this piston cylinder assembly example, you can clearly understand in which manner expansion process is taken place. Okay, so area is defined as area of this strip is defined as change in area from state 1 to state 2, and this is equal to 1 to 2 pdv. Okay, so this is the what is this is area? This is the area of this area under this process path. Okay, this is the projection of, you can in other words you can say that this is the projection of this process path on volume axis. Okay, so a comparison of this equation with equation reverse, that area under this the process curve on PV diagram is equal in magnitude to the work done during a quasi equilibrium expansion or compression process of a closed system. Okay, so suppose if you have PV curve for any process which is transferring from state 1 to state 2, so by calculating area under this process on volume axis, you will simply calculate whatever the work done inside that process. Okay, so this is the another way by which you can calculate work. Now, since in the last slide we know that we can calculate work through area under curve. So by this expression we can clearly understand that work is a path function. What is path function? Suppose here 3 points. Okay, I am explaining this to board. Suppose this is a pressure volume curve PV, and that is state 1 and that is state 2. We can connect these two stages from different paths. One path is that, one path is that, and one path is that. Okay, here I am showing you 3 types of path which is connecting state 1 to state 2. So according to last slide, in which we talk about that if we calculate area under curve, then we can get work transfer of that particular case. So if we define, suppose this is a part 1, this is a part 2, and this is a part 3. If we calculate part 1 area, state 1 and state 2, this is part 1. Okay, this is part 1. So area under this curve, this, so this is the W1. Okay, and if we calculate pressure, volume, and calculate first and second. Area under this curve. Okay, this is the W2. And if we calculate pressure, volume, state 1, state 2, like that, then this is the W3. Okay, so by these three curves PV diagram, we can clearly understand that W3 is greater than in compared to W2 is greater than in compared to W1. Okay, that means in between state 1 to state 2, in state 1 to state 2 transformation, we get three types of work. In this case, work transfer is greatest, and in this case, state case 1, work transfer is the least. So in same endpoints, we get different types of work. Conclusion is that work is depends upon path. Okay, according to path, work value is different. Doesn't matter, the end states are same. This is the key point. Okay, so work transfer depends upon path. Now we move again towards our slide. So in this slide, we can say that here are three paths. That is A path, B path, and C path. So we see in this example, WA is 10 kilojoule, WB is 8 kilojoule, and least value, that is WC, is 5 kilojoule. So conclusion is that gas can follow several different paths at its extent from state 1 to state 2. In general, each path will have a different area under it, and since the area represents the magnitude of the work done will be different for each process. This is expected since work is a path function and it is an inexact or imperfect differential. Okay, you have already seen this term, inexact differential, inside the mathematics. Okay, so that is all about path function of work. So let us take one numeric problem. What is question? An electric motor drives a tire fitted with a horizontal cylinder. The cylinder of 40 centimeter diameter contains a fluid restrained by a frictionless piston. During the stirring of fluid for 15 minutes, the piston moves outward slowly by a distance of 30 centimeter against the atmospheric pressure of 1 bar. The current supplied to the motor is 0.5 ampere from a 24 volt lead acid accumulator. If the conversion efficiency from the electric work to mechanical work output is 90%, estimate the burden on the motor, tire, and the atmosphere. So since today we have a tutorial class, we will discuss this problem in tutorial class. Okay, thank you very much.